Hello, everyone. My name is Luke Kenworthy,
And I'm Siddharth Nayak.
and we, along with Chris Chin and Professor Hamza Balakrishnan, are the authors of NICE, Robust Scheduling Through Reinforcement Learning Guided Integer Programming, created at the U.S. Air Force MIT AI Accelerator. NICE is a method for approximating and simplifying computationally difficult discrete optimization problems by using knowledge gained through reinforcement learning inside of an integer program. In this presentation, I'll first talk about the crew scheduling problem. I'll give a baseline solution to the crew scheduling problem using integer programming. We'll then talk about robust optimization with integer programming, then talk about reinforcement learning to obtain a solution, and finally, we'll talk about NICE. So first, the crew scheduling problem. We are given a squadron or a group of pilots as well as a collection of flights. And each flight has multiple slots on it, and each slot on that flight must be filled by a different pilot. Each slot also has a qualification requirement that a pilot must meet in order to be assigned to that slot. And also, each pilot has days that they're unavailable during which they cannot fly. And finally, this problem is based on real world needs. It's basically a theoretical representation of the problem faced by the group we were working with in developing flight scheduling solutions. It does differ from a lot of the literature on flight scheduling because most of that focuses on the airline industry. Okay, now I will give an integer programming solution to this problem. So we first have our sets and subsets. I, F, and S, respectively, are the sets of pilots, flights, and slots. And we have these subsets used to help us encode our constraints. In our formulation, X is our decision variable, where X sub I, S is 1 if and only if pilot I is assigned to slot S, and it's 0 otherwise. So we want to maximize the number of pilots getting assigned to slots across our solution. And we face the following constraints. First, pilots are only assigned to slots that they're qualified for. Next, they will never be assigned to flights that conflict with their leave. We do not assign pilots to multiple slots on the same flight. And every slot is filled by exactly one pilot. We prevent assignment of pilots to conflicting flights because they, like everyone else, cannot be in multiple places at once. And finally, we make the decision variable binary. So it's a 0 or a 1, and this is what makes this an integer programming problem. It's worth noting that because of our requirement that each slot has exactly one pilot, our objective function will always have the same objective value for any given problem instance. So in a sense, it's a little bit of a dummy objective function. But this uh, this formulation will help us later when we talk a little bit about nice. And finally, I think it's helpful to view this as a matrix where we have slots as our columns and pilots as our rows. And what we're basically trying to do with this integer program is solve a complicated Sudoku puzzle. So we want to put a 1 in each column, subject to all of the constraints that were given before. Okay, so now I will turn it over to Siddharth to talk about robust optimization.
One desirable property in schedules is that when there are disruptions, we need to have minimal changes in the assignments. To tackle this, we try to maximize buffers in the schedules. A buffer is the time between the end of the first flight and the beginning of the next flight. For example, a pilot is assigned to two flights where the second flight is like 2 days after the end of the first flight. If the first flight gets delayed by 3 days, this pilot will not be able to fly the second flight they were assigned to, which would mean that we will have to find a new pilot for the second flight. Now, in this case, we have a buffer of 2 days. Having larger buffers between flights helps in making schedules robust to these disruptions. To tackle this, we create a decision variable for each pilot and pair of flights where B is 1 if a pilot is assigned to two successive flights that are close together and is qualified for at least one slot on both flights. Along with this, we use a parameter called tbuffer. This is the maximum buffer size we use in our experiments. In accordance with practical scenarios, we use tbuffer equal to 2 since having delays as large as say 14 days is highly unlikely. Also, having a small buffer size helps in the computational tractability of the problem. We modify the objective function to penalize smaller buffers and incentivize having larger buffers between flight allotments. We can also use RL for the crew scheduling problem, where we can treat the problem as a game. In this game, we sequentially show the slots in the flights to the agents, and the agent has to choose a pilot for the slot. Now, note that this is quite similar to Tetris, where actions taken previously will affect the future states. Specifically, the agent might back itself into a corner by not assigning pilots optimally and then not having any available pilots for the future slots, which is quite similar to having spaces not having spaces to fill blocks in Tetris. To formulate our reinforcement learning agent, we use a discrete event space. For our state space, we encode necessary information like event information, valid pilots for the events, and the training requirements for pilots. The group we were working with wanted the pilots to progress through the qualification ranks by completing certain training requirements, and that is why we use these in our state space. Action space for the agent is choosing a pilot from the given set of pilots. And for the rewards, we use a dense reward system according to whatever objective function we want to optimize. Also, each time step in the episode corresponds to slots. Now, let's show an example for the for a particular reward structure. Here, we try to minimize the overqualification. Why do we want to do this? Many of the slots in the flights have minimum qualification requirements. That is, you need to be qualified for that flight. In an ideal scenario, we would want to save highly qualified pilots for the difficult flights and not assign them to flights which could have been otherwise fulfilled by a lower ranking pilot. As you can see, the more we train, the average overqualification gets lower and lower. This shows that the RL agent is learning to minimize the overqualification. But with perfect information, the integer programs are able to perform better in a reasonable amount of time, especially in scenarios where the constraints on objective functions can be easily encoded. Also, there is uncertainty in the environment, which means that the integer program can look at all the there's no uncertainty in the environment, which means that the integer programs can look at all the slots and assign pilots in an optimal way. Also, this doesn't work well in the robust scheduling problem. The RL agent schedules greedily where it assigns a pilot after taking a look at the current slot. It cannot backtrack its decisions, which means that any poor decision in the initial steps of the episode can cause issues in the future stages. But it's clear that the RL agent is learning something, and we want to utilize that. This is where we introduce our main contribution called NICE, and I'll hand it over to Luke to talk more about NICE.
So there are two key intuitions that allow us to utilize this knowledge used within the reinforcement learning agent. And the first is that there is a parallel structure or an isomorphism between the reinforcement learning solution to our problem and the integer programming solution. So you'll notice we have this matrix to describe our decision variables, and the columns correspond with the slots that we're assigning pilots to. And this matches exactly the time space of the reinforcement learning solution. Furthermore, the pilots used in our decision variables in the rows, as visualized in this matrix, corresponds exactly to the action space within our reinforcement learning solution. So it makes sense that there would be a parallel structure because it's used for the same problem, but we can utilize this parallel structure to kind of transfer knowledge between the two methods. And the next intuition comes from Hinton et al. In their paper on knowledge distillation, which basically says that the output layer of a neural network contains valuable information. So as we schedule with our reinforcement learning scheduler, it's picking a pilot for each slot. And what that tells us is that that pilot is the maximum over this probability distribution that says how good or what percentage chance each pilot has of maximizing future reward as we go about our scheduling process. So rather than just saying which pilot is the maximum, we now look at the values for each pilot. So one pilot might have a 50% chance of increasing future reward, and another pilot might have a 20% chance. So it is valuable to know that that other pilot is about 40% as good as our best candidate, which is the pilot that has a 50% chance of maximizing future reward. So we can think of each step of our reinforcement learning scheduler producing a probability distribution. And then what we can do is we can take this value of the probability of a certain pilot at a certain slot maximizing future reward, and we can put this into our integer program because each decision variable in our integer program, it has a coefficient of 1, but it corresponds to assigning a certain pilot to a slot. So we can replace that coefficient of 1 with a sub is, which is used to represent the probability of maximizing future reward with a given pilot and slot. And we now use that as our coefficient rather than 1. And this gives us NICE, alternatively pronounced NOICE, Neural Network Integer Programming Coefficient Extraction. And it incentivizes the agent to pick the pilot with the highest probability possible at each slot. It will only select pilots with lower probabilities if constraints forbid such an assignment. So it approximately captures the reward function used in the reinforcement learning agent while also giving it a global view of pilot assignment with the structure of the integer program. Okay, the next thing that we need to consider is how do we actually get these probability weights out of our reinforcement learning scheduler? Because you'll notice in the normal scheduling process, what we do is we order the slots chronologically. So decisions made for later slots are going to be affected, like our probability distribution at later slots is going to be affected by our decisions made previously. And we want to have a global view of the assignment, so that's an issue. So we have two ways of getting around this. The first is the Monte Carlo approach. And basically what we do is we shuffle the slots and then run a round of scheduling. And we do that n times. And for each round of scheduling, we get a probability for each pilot and slot, assuming we have a complete schedule. So then what we do is for each of those probabilities that we extract in each of the n rounds, we average over all of them throughout the n rounds. And that gives us a sort of global value for our probability of maximizing future reward, assigning a certain pilot to a certain slot. The other method is the blank slate approach. And basically, what this does is it takes advantage of the fact that the first slot that we schedule in a round of scheduling is not predicated on any previous decisions made. So, what we do is we take each slot, and rather than shuffling them like in the Monte Carlo approach, we put each slot as the first slot and then make our decision and extract our probability weights just from that first decision. Then we reinitialize the problem with another slot as the first slot. And we do that for each slot to get our probability values. And here's a diagram that shows what this looks like with the Monte Carlo approach, where we shuffle the event order, run around to scheduling. We do that 3 times. And then from those 3 times, we extract by averaging, we extract out the coefficient for each of our decision variables. We put that into our matrix or as a coefficient in our integer program's objective function, and then put that into the integer programming solver. Okay, now we need to talk a little bit about our reward structure for robustness for the reinforcement learning agent. We give it a reward of B plus 1 whenever it places a pilot that creates a buffer of size B with with any previous flights that it's assigned to. And the plus 1 incentivizes the agent to actually just make a placement regardless of the buffer. We give it a reward of capital T minus 1 whenever it assigns a pilot with no previous flights assigned. And what capital T is the length of time that we're scheduling for. So let's say we're scheduling for 7 days. If you were to put a pilot on a flight that is just the first day and just the last day, that would give you a buffer of size 5. And 5 plus 1, so 5 is our B. So 5 plus 1 is 6, which is equal to capital T minus 1. So it's sort of the maximum possible buffer reward within a given time space. And then finally, we incentivize complete schedules and punish incomplete schedules. Okay, and the way that we actually experimented with this is we first create 1 week's worth of flights. We then schedule with the integer programming baseline, the robust integer program, the reinforcement learning scheduler, and with NICE. And then what we do is 1 day into the schedule, we're going to delay F% of the flights that have not already left. And we're going to do this 100 times for each F value. And we're doing it for 25%, 50%, 75%, and 100%. And then we're going to fix delays with a disruption minimizing integer program. So it's going to create a new assignment in light of those disruptions that minimizes the number of changes to the pilot slot assignments. And then finally, we're going to count the number of disruptions that were created with each scheduling method, so fewer disruptions are better. So when we ran this experiment with a number of flights that matched the average of the probability distribution of the data we were given from the group we were working with, these are the results that we got. And this is a little bit unfortunate for NICE because the buffer integer program performed perfectly. There were no disruptions. It was able to kind of create a perfect pilot slot assignment. But there is some value here, and notice that NICE did better than both the baseline integer program and the reinforcement learning scheduler. So it was able to use knowledge, like the structure from the integer program and the knowledge from the reinforcement learning scheduler, and create something better. Uh, and it's worth noting that NICE and the buffer integer program both ran in about the same amount of time. Where NICE really shined is in the case where we had a more dense scheduling scenario. So we give it a scheduling density of 2. So if the group that we scheduled flights for would have 50 flights in a week, now we schedule with 100 flights in a week. And this is where NICE did really well. So again, you can see it did better than the baseline and the reinforcement learning scheduler. But also, the buffer integer program was never able to create a single solution for any of the F values within 90 minutes. It was supposed to create 100. So it ended up, so NICE basically has a huge time advantage here. And it was able to create its solutions in less than 2 seconds on average. So let's talk a little bit about the future. Nice, in theory, is highly generalizable. It can be used whenever there is an isomorphism between the integer programming and reinforcement learning solution to a problem, which, as you might be able to tell, is a large class of problems. So we want to be able to validate it in a variety of domains and sort of figure out which types of problems is NICE best suited to solve. We also wanted to use it to approximate nonlinear constraints in objective functions because we used it on a complicated but linear integer program. So it would be interesting to see how it would perform when we introduce nonlinearity. We also want to explore other potentially more sophisticated methods of extracting weights and generally just figure out how we can adapt the method to increase its performance. So, in conclusion, NICE uses reinforcement learning to approximate and simplify computationally difficult problems. It leverages the knowledge learned from reinforcement learning, and it utilizes the global outlook and the structure from integer programming. And we applied this successfully to robust flight scheduling. That's all we've got, and thanks for listening.